Okay, welcome to the weekly CUBE seminar. Today, we're very pleased to have Hugh Morrison. You received this PhD from the University of Colorado in 2003. He was an NCAR ASP postdoc from 2005 to 2007, after which he began his M-Cubed as an M-Cubed scientist and is currently a senior scientist. Hugh is well known for his research in cloud microphysics, feedbacks between cloud microphysics and dynamics, cloud aerosol interactions in polar clouds. Hugh has worked on developing cloud microphysics schemes in the weather research and forecasting model and a community Earth system model and CAM5. In 2012, Hugh received the AMS Henry G. Houghton Award for wide-ranging contributions to improving the understanding and modeling of cloud microphysical processes, none of which you'll hear about today. So anyway, we're looking forward to Hugh's seminar here on Cumulus entrainment and the dynamics of cloud thermals. Hugh.
Thank you for the introduction. And the only thing I think I'm going to say about microphysics is I'm basically turning it off in everything I'm going to show today. So I'm going to talk about cumulus dynamics, as the title suggests. I'll go ahead and jump right into it. I don't think I need to do much arm twisting here to convince people that cumulus convection is important for weather and climate. It is far from a solved problem, though, even from the standpoint of basic convective dynamics. A really quick Google search will show a whole bunch of papers that have just illustrated how cumulus convection, in particular convective entrainment, is important for things like climate sensitivity in global climate models. So entrainment, detrainment in cumulus clouds is particularly challenging with no clear controlling parameter or physical mechanism. And just to make sure we're all on the same page, by entrainment, this is typically thought of as environmental air that's taken in by cloud, and detrainment is the opposite. It's cloud air that's expelled and put into the environment. And I'd argue that even the concept of entrainment is somewhat nebulous. There isn't really a very clear, precise definition of it. You might imagine, for example, a situation where there's a cloud, you have ascending air nearby that cloud or surrounding the cloud, and there could be condensation in that air that would form new cloud adjacent to that cloud without any mixing process actually happening. And that would be, by kind of most measures of entrainment, considered as entrainment, even though it's not actually involving a mixing process. So just one example of this kind of nebulous definition of entrainment. So there's been some ideas for how entrainment might be related to convective updraft structure, and I'm going to talk quite a bit about that in the first half of the talk. So I want to take a step back and just think about convective dynamics from a very basic standpoint and ask the question, which provides a better framework for understanding cumulus updraft structure? And this has been something that, a question that's gone back and posed several decades ago. There's a recent, somewhat recent review paper by Junichi Yano that looked into this. And there's basically two kind of canonical models for this. One is a steady state plume, and the other is a rising thermal. So these plume and thermal models originated from applying dimensional analysis to idealized dry flows, subsequently supported by numerous laboratory studies and numerical modeling, really kind of going back to the mid-20th century. And just to formalize the definitions a bit, plumes are a buoyant jet in which buoyancy is supplied from a steady source underneath. So you get a steady source here, and the fluid in that plume rises, and the plume grows as it entrains. Thermal is a discrete rising buoyant bubble generated from a pulse source of buoyancy. So it's a kind of a blip of buoyancy. That buoyant bubble rises up, entrains surrounding fluid and grows in size, and then the fluid kind of falls in behind the wake of the thermal. So the theoretical scalings from dimensional analysis are well supported by lab studies. For example, fractional entrainment rate scaling as 1 over inverse plume radius. But between the plume and thermal models, these canonical models, there's large differences in the flow characteristics. And since this talk is focusing on entrainment, one of the important things is the fact that thermals tend to entrain by about a factor of 2 greater than for plumes. So what I talked about before, those kind of canonical models were developed from dry flows. There's at least 2 critical features for moist convection that are not accounted for by these models related to the phase change. I would say at least 2. There's many other complications for real cumulus convection, but these 2 are The fact that, of course, in clouds, you get condensation leading to latent heating, which can increase the buoyancy aloft, or particularly at the edge of clouds where you have entrainment of dry environmental air, you can get a decrease of buoyancy from entrainment and evaporation, the so-called subsiding shell that's found around clouds quite often. The earliest convection parameterizations and most current ones are based on the steady state plume framework. It's straightforward to implement. But unlike the simple inverse plume radius scaling of entrainment in the canonical plume model, current schemes use a wide variety of different methods to formulate entrainment, as well as detrainment rates, as a function of various environmental parameters or cloud parameters. And I think the fact that so many different methods are used really kind of speaks to the fact that entrainment is still quite poorly understood in cumulus clouds. So, despite the fact that most cumulus parameterizations are based on the plume framework, observations of moist updrafts or cumulus clouds that comprise bubbles or these thermal-like structures have been known for several decades. In the literature, there's papers in this going back at least to Score and Ludlam in the 1950s. More recent examples from an observational standpoint, Blythe et al. 1988, this well-known Damiani et al. Paper from 2006. I grabbed this figure from their paper. They used dual Doppler cloud radar observations, and they show this kind of neat toroidal circulation from that near this growing top of the cumulus clouds. You have this flow that looks like this, and it looks like this, kind of like a counter-rotating pair of vortices. And I'll show that's kind of like the canonical structure of these thermals. Recent large eddy simulation, LES, also supports this thermal-like view even for deep convection. So here's one example of that. I got these animations from John Peters. The cloud condensate here is shown by the colored contours. The blue and the red contour lines show perturbation pressure, and then you can see the flow vectors here. And I'm gonna restart it. So this is started from just a simple warm bubble that gets put in this simulation. There's no other forcing or anything. And you can see this pretty quickly, this toroidal circulation develops as the cloud rises up. It splits into two thermals here. There's another thermal that kind of emerges underneath. And then there's actually going to be a third thermal that comes up right here. Keeping in mind, there's no forcing or anything underneath this cloud. The cloud itself is generating these kind of multiple thermals that rise up. Now, this is in an unsheared environment. We know that most convection occurs with at least some shear. So what happens if you do the same thing but apply shear above 4 kilometers? So this growing cloud is rising into this shear layer. You still get this kind of characteristic thermal-like structure. In the sheared flow, there's this asymmetry that's introduced, and then the individual thermals are kind of shunted off in that. But you still see this kind of multi-thermal structure. Here's another one developing here. There was one over there. And if I was going to show this animation longer, I think a third one would develop right here. So that was modeling. What about from time-lapse of clouds, which I'm a big fan of time-lapse video of clouds. I always think it's cool to look at. I got this from Roelof Brunches. It's time-lapse of clouds over the UAE. I'll advance it forward a little bit when interesting things start to happen. So it starts off as this field of kind of shallow cumulus over this mountain range. It starts to develop, and you really see this bubbly nature of the convection, I think quite well highlighted in this time lapse, where you get these kind of cloud bubbles that rise up, decay, and it's just kind of a series. Eventually there's gonna be one that's really gonna rise up pretty deep, and then I think that's coming up. I've looked at this about 100 times in the past day. Yeah, there's the deep one that goes up, it decays, and then eventually this whole thing grows deep, it begins to precipitate, and so forth. So I'll stop it here. But I think you really get the idea of this bubbly nature of cumulus convection. So this thermal or thermal-like structure of updrafts challenges the steady state plume framework that's assumed by most cumulus parameterizations. People have known this for a long time. Like I said, the bubbly nature of convection probably goes back to when people were first around to look at cumulus clouds, and really, in the literature from at least the mid-20th century. So there's been some ideas of trying to unify the plume and thermal frameworks. One of the most well-known is the idea of the starting plume, which came out of the seminal work by Turner in the 1960s, where he the idea of the starting plume is it's basically a rising plume. So in terms of a formal definition, it's a situation where you have a source of buoyancy that's turned on at some time and then held steady. So you get this plume that rises up and entrains. And at the head of it, it has a structure that's basically like a thermal. And in the wake behind, it has a structure that's like the steady state plume. And quite literally, when Turner developed this model, he basically glued those two models together. However, the starting plume model is not very satisfying either because the wake behind the thermal head in cumulus clouds, so this would be like the sort of top of the first thermal in the growing cumulus cloud, itself often consists of additional cloud scale thermal-like structures. I showed from the LES animations, for example, you saw these kind of multi-thermal structure underneath. And I'm grabbing this figure again from this paper by Varbel et al., illustrating this from a 100-meter simulation of deep convection. The color contour is here in the moist static energy field, and the black contour lines that are a little bit difficult to see here are the vertical velocity. But you can see these kind of individual cloud scale thermals here, indicated by the regions of high moist static energy here that kind of rise up, but they're not just random, right? They're really organized and within the broader updraft structure. So there's a broader updraft structure consisting of these successive rising thermals.
Is there a little bit of shade over there?
In this simulation, I believe there's some, but fairly weak. I don't remember the details of it. I believe it was a case from the Darwin ARM campaign from, I don't know, it was 2006 or something. So.
Are these simulations 2D or 3D?
These are three-dimensional from Adam's paper. Yeah.
Are they precipitating?
This one, yeah, full. I take that back. Microphysics is, well, for this work that I'm doing, I'll show. In these other work, yeah, he had full microphysics on, so the clouds are precipitating. Yeah. Okay, so to briefly summarize, observations in LES suggest moist convection often occurs as a succession of rising thermals, which in the last few years we've referred to this as a thermal chain. Neither the plume nor starting plume models adequately describe the structure. So we want to ask a few basic questions. Why does this structure occur and what are the driving mechanisms? I think it's particularly interesting this occurs in the LES that are just initiated by a single bubble, right? There's no forcing that's kind of continually making new thermals rise up. There's something in the cloud that's doing it itself. Are there linkages to the traditional plume and thermal models? And then this talk is focusing on entrainment, so the obvious question, what are the implications for entrainment and dilution? So here's an example of some 3D results. These are 100-meter simulations. 6 of them are shown here. These are vertical cross-section snapshots of the vertical velocity and the color contours and the flow vectors that are maybe a little bit hard to see here. The simulations on the left have a fairly dry environment. The ones on the right have a fairly moist environment. The ones on the top here are initiated with relatively narrow bubbles. And then moving downwards, they're initiated with wider bubbles. So you can think of the ones on the top as being narrow clouds, the ones on the bottom being wide clouds. So there's a trend here. You see a transition in structure from kind of an isolated rising thermal in the narrow case, and in the dry environment, it basically entrains dry air and doesn't make it very far up, towards kind of moderate updraft widths. Particularly in the dry environment, you see this very clear kind of multi-thermal structure. You see one that's right here, one that's here, and actually descending air in between them. And then when you get to the case with moist environment and the wide cloud, you still see some sort of toroidal circulation trying to develop in here, but it has a more plume-like structure, I would say. Okay, so we can look at this in even simpler models. And these results here compare vertical velocity, which I'll call W, from a simple theoretical model and axisymmetric updraft simulations using George's CM1 model. These are not LES. This shows different simulations here. Height is here, vertical velocity is here. This is the core vertical velocity. Again, dry environment on the left, moist environment on the right, and then narrow clouds near the top, moving to wider clouds towards the bottom. And again, you see this transition going in a more humid environment and a wider cloud from a structure of a rising thermal. It's a little bit hard to see here, but there's this sort of one blip that just comes up here, sort of one maximum of the vertical velocity, to something that's like a thermal chain. And you see that in the multiple peaks of the vertical velocity field. particularly, again, in the dry environment at sort of moderate to large-ish updraft widths, and then to something that's more like a plume or starting plume in the case of a moist environment with a wide initial updraft. I'm not going to say too much about the theoretical model. People can look in this paper here, but I'll just mention that it's a lateral eddy mixing model that assumes linear horizontal gradients, so linear gradient between basically the cloud core and the cloud edge. But the key thing here is that, I won't go into the details on this, but the gradients in the model are essentially enhanced as a function of the vertical gradients of vertical velocity. So you have convergence where there's strong vertical accelerations, and that sharpens the gradients in this model, which results in enhanced mixing and a larger implied fractional entrainment rate. So as a result of that process, you get, even in this relatively simple model, a complicated structure of fractional entrainment rate, which I'll call epsilon here. And that's illustrated here. So this is just taking the dry environment here, moist environment here. These are vertical profiles of the fractional entrainment rate. And the three different colored lines here are just three different times with the growing cloud. So the blue here is kind of early on, green is after a bit of time, and then red is after a bit more time. The cloud top here, for example, in the case of the red, near the top, there's a point at which the vertical velocity gradients are zero, right? Because that's where you sort of get the maximum vertical velocity, and then it has to go to something that's small, or in the theoretical model, zero in the environment. So as a result, you have relatively weak mixing, small fractional entrainment rates there. You get, as a result, little dilution of buoyancy, sort of rapid acceleration and large W. But below that, it causes larger vertical velocity gradients, which then, from this model, lead to more fractional entrainment. So you get that jump up here. And of course, we have to assume something about the physical length scale of that, and that's related back to R, and that comes from some theoretical ideas and then some of the LES modeling that determines those scales. So you can think of these as corresponding with individual thermals, where the thermal center would be like here, where you have the maximum vertical velocity, and then the bottom of the thermal would be down here, where you have that inflowing air around that toroidal circulation. So in this theoretical model, there's this close correspondence between enhanced entrainment and mixing, which brings in dry environmental air, and the key is dry environmental air, because that leads to dilution of buoyancy. And as a result, that changes the vertical velocity and then the flow structure. So it's kind of close correspondence. And one of the advantages of a very simple model like this is you can just piece it apart, because it's just a set of equations, and figure out what's driving what in it. And you can show that this chain structure is a result of this really kind of jagged thing, is a consequence of the moist thermodynamics or the phase change. You can run this model by turning off essentially the effects of phase change from dry air entrainment, and it produces a structure that basically just has a constant with profile of fractional entrainment rate, which going down here in the moist case, you can see it's much more constant because of that. It's just the effects of dry air entrainment and the resulting phase change are smaller. So other studies have talked about this kind of, call it jagged structure, or this enhancement of fractional entrainment rate at the bottom of the individual thermals. This is a nice paper by Moser and Lasher-Trapp, published in JAZ a few years ago, where they looked at this kind of structure of fractional entrainment rate. So fractional entrainment rate here is shown on the bottom of these plots on the x-axis, height is on the y, and these are at 4 different times. And you can see here, you can actually trace the individual thermals. The bottom of the thermal here is where you have this enhanced fractional entrainment rate. It's about a factor of 2 to 3, if you can think of kind of a background entrainment rate being here. And you can just track that thermal as it's rising up. And like I said, you commonly get a succession of them. Another one forms here. There's actually an earlier one that's forming here that then kind of dissipates up here. So we looked at this kind of structure of fractional entrainment rate a bit more using LES and the ROMPS method for doing a direct entrainment calculation. So this shows 6 different runs in different conditions. Again, a dry environment left, moist environment on the right, narrow clouds up top, wider clouds near the bottom. And the color contours here are the fractional entrainment rate. Darker red is a larger entrainment. And particularly, again, in this dry environment and kind of the middle-sized or middle width of, middle to large width of updrafts, you see very kind of prominent streaks. Those are the enhanced entrainment that you're getting in those toroidal circulations at the bottom. You can kind of trace those up. they rise up about half the speed of the maximum vertical velocity within them. We'll talk a little bit more about the structure of the individual thermals a bit later. As you get to wider ones, there's some streakiness, but it's not as prominent as here. Again, that's kind of more like this, more plume-like updrafts. You can calculate detrainment rates in a similar way too. The structure is actually quite different in detrainments, much less streaky, so to speak. You get large detrainment rates up near the cloud top, where you get these individual thermals kind of rising up, undergoing kind of massive detrainment and then decaying. Yep.
Can I interrupt you? I just cannot resist. Is the key aspect the fact that you actually increase buoyancy through condensation, that you have this volume, and you haven't mentioned that, and I'm curious because in my mind that's always the key, that condensation typically gives an increase of buoyancy with height. So when you think about the volume that rises, it actually accelerates. So it has to, that's where the toroidal circulation comes from. I always thought
We thought that first
Excuse me,
too.
could you repeat the question for the
Oh,
home,
yeah.
for the home audience?
So Wojtek's question was, in terms of why, I'll just rephrase it slightly, in terms of why you get this sort of succession of rising thermals or this toroidal type of circulation, is it just because you simply get condensation, latent heat aloft that drives an increase in buoyancy so that everything accelerates upwards? And that's what we thought at first was going to be the driver, but it turns out it really wasn't the case. So the plume-like updrafts, if I can go back a little bit here, these actually have the strongest vertical velocity because they're entraining less. So both from the LES, the simple axisymmetric model, and the theoretical model, it's showing that dry air entrainment is really the key to getting multiple thermals coming up. Otherwise, it kind of just looks like a starting plume. So you still get that. In this one, you still clearly see the toroidal circulation kind of near the head of it. You still get that because you have strong buoyancy gradients, vorticity generation near the top of it, but you don't get that kind of chain-like structure underneath. That really seems to be a function of the dry air entrainment. So again, one of the advantages of the theoretical model is that it's very simple. So we can probe it and see, what's causing what here. So this just shows correlations of fractional entrainment rate with various parameters from the model. And I want to point in particular to the vertical velocity W here. So vertical velocity is on here, epsilon, fractional entrainment rate is here, and then buoyancy. And you can see a negative correlation here, particularly in the case of the buoyancy. So we can look at cause and effect here. And if you first look at this, you might think, well, those are anti-correlated. Perhaps W and buoyancy are somehow inversely related in driving a decrease in the fractional entrainment rate, right? And that argument has been made before. You can decrease fractional entrainment rate and dilution from increased vertical velocity just because the parcel has less time to mix as it's rising up, if it's moving faster. Turns out in this model, that's not the case, though. It's the other way around. Larger fractional entrainment rate, primarily driven by this inverse dependence on R, which has the strongest correlation by far in the model. So larger fractional entrainment rate is driving the decrease in buoyancy and, in turn, vertical velocity. There's a small decrease directly from momentum entrainment as well, but that's pretty small in this model, and in other LES studies have shown that too. So the key point here is that there's always a difficulty, I think, from separating causation from correlation. You get these complicated systems. Even in just looking and analyzing LES data, it can be really hard to sort of piece that apart. And I'm going to have a bit more to say on that in the last few slides of the talk. Okay, so I'll take a breath. I've been talking a lot. I need to. Okay. Hopefully, I've convinced you that cumulus convection often has a thermal-like or multi-thermal structure. So the second half of the talk here, I'm going to focus a bit more on the dynamics of individual thermals. So we can ask things like, what's the flow structure like? How do they entrain, drag, etc.? So the overall flow structure strongly resembles a ring vortex. I talked about the toroidal circulation already several times. This is actually quite similar to Hill's analytic spherical vortex. This is an analytic solution to the Euler equations. It's a very simple system. It's just steady state, a vortex kind of moving upwards. There's no buoyancy in it. It's a very simple system, but it turns out the flow structure of buoyant thermals is quite similar to that, and even cloud thermals, not just dry buoyant thermals, but moist cloud thermals as well. So there's some papers in the last 10 years that have talked about this correspondence. One, for example, by Romps and Charn, 2015, where they composited a bunch of cloud thermals from LES of deep convection. and then looked at the stream function associated with that, and then the pressure perturbation is in the color contours here. Compared that with Hill's vortex, you can see a pretty close correspondence here in the stream function. The pressure field is a bit different here, and that's primarily because of the impact of buoyancy. They included the buoyant perturbation pressure component in this. So that's why you get this kind of positive over negative structure. So we've looked at this as well. This is some in a paper that we recently published looking at the drag on actually dry thermals. And you see a kind of similar structure. It's a little bit hard to see the streamlines in here because I showed the vorticity field in here too, showing that you get this kind of cool looking turbulent structure to it. But the streamlines are very similar to Hill's vortex as well. It looks kind of spread out in here, but that's actually just the aspect ratio here. It's quite similar to Hill's vortex in shape and the flow structure internal to it. So we can look a bit more at entrainment of dry thermals. The fractional entrainment rate is closely related to the thermal spreading rate in terms of the radius or the volume. In this case, I'll mainly talk about the spreading rate of thermals. That's the increase of thermal radius R with height Z. It turns out that entrainment is quite negligible in dry thermals. There's a nice paper by Lacone and Givenchy that shows that using direct numerical simulation. One can assume self-similarity so that the thermal shape sort of is constant as it's rising up, and apply dimensional analysis to show that dRdz should be a constant. So that is supported by many lab studies and numerical modeling, going back to the mid-20th century. Some work that we're currently doing is showing that here, the thermal radius for dry buoyant thermals is shown here, for height is shown here. And this is for different initial aspect ratios of the thermals. And you can see a relatively constant rate. It's a little bit noisy, but fairly constant as the thermals are rising. For dry thermals, entrainment is driven by organized inflow from the bottom of thermals. So going to this kind of simple picture here, you have this toroidal circulation like this. The fluid is drawn in from underneath, and initially, it's just for example, for an initially spherical thermal, the buoyancy field is just a sphere, but because you get the structure of the toroidal circulation that develops quickly, the buoyancy gets swept out in the center first, and the buoyancy then, positive buoyancy, gets confined over the centers of rotation, which are here and here, in this 2D kind of slice through the thermal. As a result of that, you have baroclinic generation of vorticity here. It generates vorticity this way. In this, it's here, but because the flow is around the thermal like this, the vorticity increases here, it decreases here in terms of magnitude, and the whole thing spreads outwards. So it's kind of a cool feature, and it's directly related to the fact that the buoyancy distribution is like this in dry thermals. Somewhat interestingly, the basic mechanism of this entrainment is similar for laminar and turbulent thermals, at least up to the Reynolds number of 6,300 that they were able to model with direct numerical simulation and the Lacone and Givenchy paper. So for dry thermals, numerous studies have shown that thermals that are initially spherical and at rest have this spreading rate is about 0.12 to 0.15. So you might ask why that particular number. I should mention that that's in incompressible Boussinesque and neutrally stable environment. That does affect that, the spreading rate. So the spreading rate is sensitive to initial thermal shape. Flattened thermals tend to entrain more quickly than elongated ones, and I'm going to talk about why that is. So from that, we can think about two particular questions. Why this particular value of dRdz? Why is it that and not, 0.05, 0.01, 0.5, whatever? So there's something happening in the dynamics of this that result in that particular number. That number has been demonstrated by umpteen studies. And then why the sensitivity to initial thermal shape? So that sensitivity is illustrated here in this paper by Lyodol 2015. They show, they call it L over D, but this is just the aspect ratio. By aspect ratio here, I should mention this is defined in terms of the vertical length divided by the horizontal width. So these are elongated thermals, and these are the flattened thermals. And like I mentioned, the flattened thermals have, you see this sharp increase they call it alpha, but that's just defined as this dRdz. So the spreading rate increases sharply as the aspect ratio decreases below 1. So we wanted to look into why, addressing those two questions, why these things are. So we developed this analytic model of thermal vertical velocity. And by thermal vertical velocity, I mean the ascent rate of the thermal as a whole, not the parcels embedded in it. Excuse me. And this is based on essentially the thermal vertical momentum budget, and you can rearrange the terms, make some approximations, and you get something that looks like this. I'm not going to go through what all these parameters mean. I will mention that there is a dynamic drag coefficient in here. That paper that I mentioned that we recently published in JAZ, we showed the dynamic drag coefficient for both laminar and turbulent dry buoyant thermals is about 0. I won't go into further detail on that. So we take and neglect the dynamic drag coefficient part of this here. And then we can take, I should first mention, so you can compare this analytic model with numerical simulations of the spreading rate of dry thermals. And that's done over here. Again, we're using the CM1 model with different aspect ratios as shown here. This is all non-dimensionalized, so no units. And the results in the simulations are in solid lines. The analytic model is in the dotted line. So it compares quite nicely over this range of aspect ratios. So one thing we're interested in particular is this point here, the height at which the vertical velocity is a maximum. So below that, the thermals are spinning up. Above that, they kind of reach this steady sort of period where there's a slow decay in vertical velocity. That scales as the time to the 1/2 power. There's been previous papers that have talked about that scaling in this sort of steady phase. So we could take d by dz of this analytic equation, set it to 0 to find this height of the maximum, and then solve for alpha to get an equation that looks like this. So this shows a 1-to-1 relation between this critical height, where the spin up is happening, and alpha. In other words, if we know that critical height, we can find what alpha is. And if we can understand the mechanisms that are controlling that critical height, we can understand the mechanisms that control that value of alpha. Again, alpha is the dRdz, the thermal spreading rate. So what determines z crit, which again we interpret physically as the height where the thermodynamics are spun up? So we can look at this in terms of going back to that model of a dry thermal, the idea that what happens is that the buoyancy is swept out of the center. So these are just vertical cross sections of one of the simulations. With time going down this way, the buoyancy field is shown here, vertical velocity in the black and dashed, the solid and dashed contour lines. Again, parcels down here initially get swept through the toroidal circulation via entrainment and sort of wipe out the buoyancy in the center here. So the point at which that buoyancy is wiped out of the center, then the buoyancy is confined to the rotation centers, the vortex ring, and then it's essentially spun up. That alpha parameter is then sort of baked in, as it were. So the time scale that it takes for that to happen is the time for a parcel that's initialized or initially at the bottom of the thermal or just below the bottom of the thermal to ascend through the thermal to near its top. And it turns out that that is a linear function of the aspect ratio. So in other words, a flattened thermal, it takes relatively less time because it just doesn't have that far to go vertically, versus an elongated thermal, it takes a long time because it has to go all the way up there. And you can show that the coefficient of that linear relation is a function of the mean parcel vertical velocity to the ascent rate of the thermal as a whole. And that's relatively constant in all these simulations, not a function of aspect ratio, has a value of about 7/4 or 1.75, which interestingly enough is in line with Hill's vortex. So I talked about how the overall flow structure of these resembles Hill's vortex, and this is kind of an illustration of why that's important. So it sort of determines how, the ratio of ascending parcel, the velocity of ascending parcels in the center to the ascent rate of the thermal as a whole. So when we use this relationship for z crit as a function of this aspect ratio, plug that into this equation right here, we get the black line right here. The simulated values, these are just directly calculated spreading rates, just directly from the simulations. It lines up quite closely with those. And you can see this characteristic, in this case, it's about 0.13 for that alpha. So it falls right in line with that 0.12 to 0.15 that I mentioned before. And then it increases with smaller aspect ratios sharply. A slower decrease as the aspect ratio increases. Eventually, when you start getting out here, sort of funny things happen. They get really elongated like this, and they begin to detrain buoyancy out the bottom. So I didn't extend it past 2 because you get sort of features like that. And that Lai et al. Paper that I mentioned discusses that aspect in detail. Okay, so this provides a fairly complete picture of entrainment in dry thermals, but that was a bit of an excursion. This is talking cumulus dynamics, right? So you're probably wondering, well, that's all good and well, but what does this actually have to do with anything that I'm interested in? So we can ask, well, what about moist thermals?
I have a
Yeah.
question. You perhaps you mentioned this, but all those dry simulations were for unstratified environments? Or?
Yes. Yeah. Yeah, that's a pretty important point. Yeah, so thanks for bringing that up. Yeah, all unstratified environment. So we did this comparison between dry versus moist thermals. This is not unstratified anymore because it's hard to get a moist thermal in that case, right? So we tried to make this as apples to apples comparison as possible. We had to think pretty carefully about how to do this. It's not too obvious, but we did this in as apples to apples comparison or an apples to apples way as possible. So we can directly compare the spreading rates. And it turns out the thermal spreading rate is much smaller for moist thermals, about a factor of 2 compared to dry thermals. And this is a direct consequence of their different distributions of buoyancy inside of them, and thus that baroclinic generation of vorticity that's responsible for the spreading of the dry thermals, like I talked about before in this diagram. So this shows plots of the dry and moist thermals and their buoyancy distributions when they've risen. This is, I think they're initialized around a height of 2, a radius of 2. So, this is after it's risen about, I think about 8 radii. And you can see here, this buoyancy, again, is mostly confined to where to the vortex ring here, where you get circulation like this. This is just showing half the thermals, by the way. This is a cross-section through the center. But in the moist case, where you have condensation and latent heating, you see much higher values of buoyancy overall, but in particular, higher values of buoyancy right in the core here. And because of that, you don't have that same distribution of baroclinic generation of vorticity, and you don't get that outward spreading of the vortex ring.
To clarify, moist is stratified. All right?
They both are.
Both.
Actually, yeah. Yeah. So this actually shows the volume growth rate. You can think of this as being, somewhat analogous to the radius spreading rate. As a function of height here, the volume is down here of the thermals. The black line here shows the moist case. The dry case is in red, which is a little bit hard to see underneath all these lines. It's a little bit easier on this plot here, but you can see that quite large difference. So we thought there's kind of 2 competing hypotheses that might explain this. One is that, okay, there's just a lot more buoyancy in the moist case, clearly. So these are not non-dimensionalized in the buoyancy field. These are actually dimensional units. I don't have the scale on here, but the buoyancy is a lot larger in here, in the red colors than over here. So we thought, well, let's take the dry thermal case. Let's add heating artificially into it to basically make the total buoyancy of the thing match with what the moist is. But let's spread that around the whole thermal. And that's what these different lines here are. It basically makes no difference on the spreading rate or entrainment rate of that. So it's not the buoyancy magnitude here that matters at all. It is the distribution of it, the spatial distribution, that's the key. So we did that same thing with the dry thermals, only now we took that latent heating and concentrated it in the core of those thermals. And indeed, you get something that's actually much similar, or quite similar to the moist case. It's even a bit less entraining up here. And the reason for that is because as you move upwards in the atmosphere, the latent heating rate goes down, right? Because it's getting colder and colder. So that really sort of demonstrates how this buoyancy distribution really impacts the entrainment rate here. And this just shows a conceptual diagram of that. Yep, George?
This is no sedimentation, right? It's just like reversible.
Reversible microphysics, yeah. This is one of those examples where I said I'm going to turn microphysics off. Yeah, definitely no microphysics in here. And on top of that, I turned off, there's no microphysical impact on the buoyancy. So it's only related to to the temperature field in this case. I turned off any water effects, condensate on the buoyancy to try and make it a bit more of a fair comparison. Okay, so I just have a few more slides here. I should be able to wrap up here in a couple of minutes. So what we've learned so far, cumulus clouds are typically composed of thermal-like flow structures, often organized in clusters and rising in succession. Again, this thermal chain idea. The thermal-like structure of cumulus seems to have an important impact on entrainment. I talked about those pulses of locally large fractional entrainment rates near the bottom of individual cloud scale thermals. Of course, there's all kinds of scales of thermals in these, right? If you look at, for example, vertical energy spectra in clouds, in cumulus clouds, you don't get this sort of break in the spectra. But the point is that these are cloud scale thermals that have this kind of large pulse and fractional entrainment rate, or lead to that in their convergent flow of their toroidal circulations. Advances have been made in understanding the dynamics of dry thermals. These are relatively well understood, I think. But while there are some commonalities between dry and moist thermals, like the general flow structure, that toroidal circulation that resembles Hill's spherical vortex, results for dry thermals don't necessarily translate to moist thermals. Specifically for the entrainment, I talked about how there's those large differences because of simply of the differences in the buoyancy distribution from the impact of latent heating from condensation. So this is kind of a take-home point here. Cloud thermals are their own beast. You can't just model dry dynamics or dry thermals and say, okay, now we can just translate this directly to moist thermals. That's not really true. So I want to have a couple of points here at the end in the form of questions. As I talked about, the dynamics of entrainment appear to be different for moist and dry thermals, but we know we know that moist updrafts entrain, obviously. Most clouds are pretty highly diluted. So this kind of brings up a question: is turbulence more important for the dilution of moist thermals than dry thermals? I talked about before, at least for that range of Reynolds numbers that the Lacone and Givenchy study looked at, the entrainment rates were not very different, and the entrainment process in the turbulent thermals was very similar to the laminar thermals. This is actually consistent, the idea that turbulence is maybe more important for moist thermals, with some results from a recent paper. Might still be impressed by Sarvedal in 2022, where he looked at direct calculation of entrainment and detrainment, showing that they're large, but they mostly balance one another. So there's all this kind of smaller scale stuff happening. You can get entrainment events that are coming in that air can sort of immediately detrain, which maybe doesn't even matter that much. But the point is you get kind of all this smaller scale stuff happening that might be important in the dilution process. But I think that's still an open question. The importance of that versus this sort of more organized entrainment that's happening like in the dry thermals. So if that's true, if turbulence in smaller scale mixing is more important, we can ask how much of the entrainment variability that we see is simply from the quasi-stochastic nature of entraining turbulent eddies. A lot of people have posed entrainment as a stochastic process, even and developed parameterizations based on that. And some of that here, I grabbed this figure from Hernandez, Deckers, and Sherwood paper, where they looked at correlations through different environmental parameters, and all the correlations are pretty small. The inverse radius dependence was the largest one, which is on the leftmost here, but that only explains about 20% of the variance. There's, again, this issue of correlation versus causation that I think is quite important in interpreting any kind of relationships or factors that control entrainment. I gave the example of the relationship between fractional entrainment rate and vertical velocity or buoyancy. I think that should be looked at more, though I wouldn't take my word for it that it's the fractional entrainment rate that's driving the changes in W and B. There still could be an impact. That was a highly idealized model, right, that I looked at in that. So it'd be good to investigate that question more. And this is a bit of a broader point. Compared to idealized LES under controlled conditions, a simple eddy diffusion model works, and I would say perhaps surprisingly well for representing some key aspects of cumulus dilution. I talked about the theoretical model before that was based on eddy diffusion model with some modifications to account for changes in gradients. But even if you get rid of those modifications and just use an even simpler eddy diffusion model, it can actually reasonably capture key features of cumulus dilution as seen in LES. These are 50-meter simulations, but under controlled conditions. So these are actually a little bit more complicated than the LES I showed earlier from some of our work. Instead of initializing the convection or initiating the convection with a warm bubble, we're initiating it with surface fluxes, but we can control the size of the clouds by the distribution of those surface fluxes. And that's what I mean here by cloud width is constrained. So this shows maximum buoyancy and the cloud equilibrium height. That's just the maximum height inside the cloud where the buoyancy is larger than, or which, at which the buoyancy is larger than 0. On the x-axis here is essentially the subcloud updraft width, which is very strongly correlated with the cloud width above, or the width of the cloud above its base. The lines here, the different colors here show results for different free tropospheric relative humidity. Red is 90%, green is 60%, blue is 30%. The lines here are from just that simple mixing model. The crosses here are from a large ensemble of the LESs. And you can see a pretty reasonable correspondence here between these two. Again, perhaps surprising that it's simple, but it seems to do an okay job. So this is just that same comment from 2 slides ago, but we can maybe add some questions. If that sort of situation is modeled quite well, what are the other critical missing pieces? And how do we even know when we've gained sufficient understanding of basic cumulus dynamics? How much of the problem, how much uncertainty is due to a lack of basic understanding versus the kind of external controlling factors? I pointed to the example here of the cloud width or the radius being quite important here, but then the obvious question is what controls cloud radius, right? And there could be a billion different relevant length scales that might impact that. So this is kind of an epistemological question, but I think it's maybe an important one. How do we know when we really, how do we know when we know cumulus dynamics? And I'll end on that.
Okay, thank you. We're open for questions, comments. Morris.
I had asked the first question since you're my son, right, Morris? Sorry. I've been waiting for years to try that one out.
Yeah, you've never used that one before.
Nope. No. Okay, so the question is, from what you've learned so far, how would you impact convective parameterizations as we now know them?
That's a really good question and a really tough one to answer. It's actually, there's a pretty obvious reason, I think, why people starting back in the 1960s developed parameterizations based on the plume model, right? They knew back then that convection was bubbly. That's pretty obvious, right? But it's just a lot conceptually easier to implement it in that kind of framework. For one thing, the d by dt, the partial by partial t terms go away because it's steady state, right? So you can imagine trying to build a thermal-based convection model. And so people are thinking about this. I'm not as involved in that work, but it's not super obvious to me how that could be done, or even what the ramifications of it might be. Like you saw in this work, it's suggesting you get these pulses of entrainment that are kind of localized at the bottom of the individual thermals. But the question is, well, how does that really impact the overall, height that the plumes reach or things like that? And as I showed in this slide right here, maybe you don't even need that to model some important things like the cloud equilibrium height, which doesn't have that effect of that kind of thermal enhancement of the entrainment.
Also, wouldn't it be kind of true that as the convection began to precipitate, become more of a convective storm per se, it might actually produce more of a plume-like structure because it's forcing from underneath and cold pools?
Yeah, that's exactly right. I mean, cold pools will themselves introduce another length scale in, and there's been several studies. I'm thinking of, for example, Krotnoff and Randall, 2006, had a pretty widely known paper where they argued that convection just couldn't get going very much because the cloud thermals or the cloud widths were small, but then once they started to precipitate, all of a sudden they got a lot wider and were able to go deep. So yeah, that might be an important part.
To follow up with my comment about the buoyancy increasing, now if you go to the stratified environment, there's another aspect which I think you can see in some of your figures, which is why thermals in stratified environment develop this lag, as I would call, like the atomic bomb lag is kind of classical example of that, I think. And the argument is that, of course, when you develop this circulation, then you bring the fluid from the bottom, And at some point, of course, it is kind of negatively buoyant because you drag it up from this in the stratified environment. So there's another kind of a leg that wants to go down. So I think there's another complication when you go from unstratified to stratified environment. It's kind of another twist to the story, if you like.
Yeah, I mean, precisely. That's just yet another thing that kind of adds the scales. I think in particular, though, this is interesting from the standpoint of the toroidal circulation, which on the outside of it, in the stratified environment, it's having to push down stratified air, and that seems to have some importance on what's happening as it's coming around in a highly stratified environment. It might not sort of make it very far, right? Which can impact downdrafts in particular. I didn't really mention downdrafts. I don't think I even used that word a single time, but that to me is a really important aspect of a lot of this is just downdraft dynamics, which are understood even less than updraft dynamics, right? So we actually have an ASR project starting up to look at downdraft dynamics as well, but I think the stratification is not surprisingly, a really critical element for that in particular.
Yeah, so a good fraction of the time, the cumulus cloud initiates at the top of the boundary layer. So it would seem that the boundary layer structure would have a fairly significant influence on at least the initiation of convection. But you haven't really talked about the fact that maybe the properties of the boundary layer are determining this initiation. So do you have anything to say about that?
Yeah, absolutely. That's a great comment. I think there's this idea that, again, that's introducing more linked scales on the problem. I mean, the simplest one is PBL height, and there has been work, including Wojtek's paper back in 2006 on the LBA intercomparison, which linked the initiation problem to the fact the boundary layer is growing deeper, the eddies in that are growing larger, and maybe they finally grow large enough where the cloud is large enough that it can go deep, because once it's large enough, it can have reduced entrainment. So yeah, all that ties into it. I think it's a really complicated problem because it's at the intersection of all these things. It's hard to really sort of remove any one thing where you can say, oh, that doesn't matter at all for cumulus convection. It kind of involves everything.
Do I need micro? Yes, you do.
I guess, we can discuss about general issues later, I suppose. I think better to get back something concrete, and I guess something interesting, but you didn't explain the point you showed. It was scatter plot between entrainment rate and bunch of variables. Could you go back? It's
Yeah, I'm
kind
not
of
sure which one
end
you're
of
talking
first
about.
half.
In the first
And
half.
I already forgot what, yeah, that's one.
This one.
No, next,
This one?
two more later. Next, I think. No, which way you're going? You go
I'm
forward.
going backwards.
That's one, that's one.
Yes.
Well, this is full numerical simulation, right?
No, this is from the theoretical model. So this is from the simple model.
Oh, that's where I got confused.
Yeah. I should have made that a little more emphasis on here. Yeah, so the main point here was that the theoretical model, despite its simplicity, is actually able to produce a lot of scatter in the results.
Except for plot of B over W square.
Yes, that's true.
I guess, well, my guess is this is consistent with similarity solution.
The
B over W square.
That's a really interesting one, and I do have a slide on that.
did
We can maybe
back
talk
up-
about this after too.
Yeah. So I thought that's something good. Get back. Yeah. Well, I wouldn't stop otherwise.
I did want to say something about the B over W squared, so I actually had a slide on it. We can go through this slide later,
know
though.
what?
It looks like we probably have to wrap
Starting
up. pretty
today,
soon.
we're going to repair to the refreshment room, and we're going to
Okay.
continue talking about all this. But since
Can
we have a time limit, we have to address some
Oh,
of
can I just mention one other thing with the B over W squared? There is a reason why it has that thing, and it actually has a strong correlation if you segment it by height. But we'll talk about that after, Junichi. Okay.
Okay, so we got a few questions here on Slido. Clarification, just to clarify, based on earlier observations, the LES studies, entrainment rate is usually quite large in a cloud base. Your theoretical model doesn't seem to be the case.
I didn't quite.
And it said, part two, the thermal chain model is rather idealized. Is there any effort to compare model simulation to more realistic observation convection like BOMEX?
Yeah, that's a good question. There's actually a very simple answer to that. It's because in the theoretical model, we actually don't assume a mass flux at the base. We assume the vertical velocity is 0 as a boundary condition. So, one of the reasons it's large in LES studies and other studies is because the mass flux is small. Fractional entrainment is entrainment divided by mass flux. You get a big number. That's you get this strong peak right at the cloud base. But that's not in the theoretical model because of that boundary condition.
One here from Andy Prine. Can this work inform how to, where to go? Oh, there, it went up. Inform how to treat entrainment, detrainment, and kilometer scale models that do not use deep convection scheme, but they're generally not entrained enough. That's sort of a form of Morris's question, I think. What do you do about, how do you use this for?
Yeah, so a little bit. I mean, this is on kilometer scale models, not convection parameterizations. But I'm not sure. Like, I think honestly, I think that's my answer. I think there's something that could be informed with that, but there's another important aspect to this besides the entrainment problem that I didn't talk about at all, but I worked on that quite a bit about 7 or 8 years ago, and that is just the basic non-hydrostatic dynamics of the problem, where you get a compensation of the buoyancy and buoyant pressure when the updrafts are flattened like pancakes, right? The vertical velocities are just suppressed in that
More
case.
hydrostatic.
Yeah, exactly. So that can also be a really important factor once you start getting out in kilometer scale and larger models, which kind of fits with the idea that those models sometimes they have a hard time kind of getting going, but then once they do, they go and everything kind of goes,
Right.
because they're not in training as much. So it's kind of
Right.
compensation
And they
in some
still
ways.
feel the instability, so they can take off once they get going.
Yeah.
Okay, further, another 2 minutes here. So I always thought about the moist problem. We have very unstable flow. In the middle of the plume, where it's releasing latent heat, it becomes much warmer than the starting thermal, and it kind of takes off like a rocket and leaves and has its own circulation, toroidal circulation. And if it keeps on doing that, it's releasing until it gets to the level where it has a lot of excess buoyancy. Then it can keep on having these episodes of kind of taking off like a rocket. I don't know how that's related to the entrainment.
Oh, well, this is pretty much Wojtek's question, I think, from earlier, and I'll.
Okay. Well,
Yeah,
I didn't understand it.
I
So
think
I understand my question.
I think the basic answer is that if you don't have the dry air entrainment part, it basically looks like a starting plume. So you get this kind of accelerating thing with this plume-like wake behind it.
All right.
But something with the entrainment of dry air is affecting that structure underneath of it and generating these leading to these pulses. The other kind of interesting thing here related to that and Wojtek's question is what sort of continues to generate the ascent at the cloud base? You got to lift parcels up to the LFC, otherwise the whole thing will die off. But it seems like the clouds basically do this on their own. They generate a pressure, or they have a pressure structure that's associated with accelerations up and in. Even in unsheared flow, right? You can get buoyancy pressure that can draw that air in.
But it
underneath
can't
of that.
happen. It can't continue. Can
Not
it?
forever.
Not
Eventually,
forever.
because
Yeah.
they'll be cut off as you get subsidence around them and stuff. And this is, of course, precipitation probably cuts them off before that would even happen. And not to mention you get organization of convection, shear affects everything else. But yeah.
Okay. Well, thanks. Let's thank you again for a stimulating talk. And we will. Those of you who are interested, you will be available for further grilling in the refreshment.